So today I'm really pleased to have Professor Bowman talking, and he's actually a distinguished service professor. He got both his bachelor's science and his master's science degrees in physics and mathematics at the University of Auckland in New Zealand, and then he moved from the
Antipodes.
From that lat to way north, and went to Saskatchewan in Canada, where he got his PhD in engineering physics. He joined MSRC in 1971, and he actually served as the acting dean and director during 1987 and 88. So he's the coordinator of the storm surge group, whose current interests are prediction and modeling of storm surges that threaten New York metropolitan areas. And he's been saying for the last 30 years, you're going to regret not doing something, and that will come to pass, I'm sure, in your lifetime, Malcolm, and your tenure here. Possibly. Okay. He's also coordinator of an international group of oceanographers and modelers who continue to study the Black Sea.
It's a gleam in my eye. I'll tell you about it.
All right. So that is what he's going to tell us about today. So, Malcolm.
Thank you, Josie. I have a tendency to wander and get distracted, so if you see me sort of wandering off the topic, just sort of wandering. So I'm going to tell you a story that goes back quite a few years, and but before we do that, I have to have an admission to make. I'm going to give a talk about the Black Sea, but I have never been to the Black Sea. I have never seen it with my own eyes. So if you think I'm kind of, this is going to be fake science, you can leave now. Also, you probably won't learn very much about hypoxia and anoxia. I mean, I'm a physical oceanographer, so if you want to leave now, I won't be offended. But what I do have is actually, in one of these two bottles, I have some Black Sea water, and I'm not sure which. I'm not sure which bottle. This one says St. Petersburg vodka duty free. So I think maybe this is the vodka. But where did this come from? Well, I had a student years ago who was from the Ukraine, and she came here and did a degree. Can't remember her name. Then she fell in love with an American student here at Stony Brook. Might have been in SoMAS, I can't remember, and they got married in the Crimean Peninsula in what was then Ukraine, and she brought me back this water. So I've treasured this, and we'll see if it's the real thing, right? So, no. Oh, where's Marat? Is he here? He's the only one who can speak Russian. You can't read it. Here, don't break it. So, all right, so. Those Russians can drink, I tell you. So, I have to be a little.
Yeah, can you check the battery on the wireless mic? Or you can just move it down.
I think it's too loud, Tom. Now it's all tangled up in these things.
Excuse me. Yeah, the battery's fine. Yeah.
Well, I don't know if this is old or new.
The other thing.
You never see anybody check a 9-volt battery like that? Give me a second.
Malcolm, we're already out of control.
Now you get a memorable seminar.
So I have to be careful what I say today because, according to Mark, this on all our seminars streamed worldwide on the internet, and one of my collaborators I'm going to introduce you is sitting in his home in Moscow right now. Hi, Konstantin, can you see me? I don't want to attract the attention of the NSA. So, anyway, so let's get started. Way back in about 1987, well, you can turn the light on. I haven't got the slides going yet. We may not even get to the slides. I think it was 1987, before some of you students were even born. I got a cable. This was the days before emails. I got a phone call to my office from a very large Soviet research ship called the academic Kurchatov that was plying the North Atlantic. And in those days, in the waning days of the Soviet Union, there were very few ports that would welcome a Soviet ship. I mean, you could go to Havana, Cuba, and probably Venezuela and a few other places. So these were huge. This was a huge ship, 50 scientists, 50 crew, and they would go to sea for up to 6 months at a time. So they had huge diesel oil tanks and so forth. I got this cable from the chief scientist, and his name was Rostislav Osmedov, who was a very famous Russian oceanographer with expertise in ocean turbulence. And he had worked with our very own Akira Okubo across the Iron Curtain. They collaborated and they published papers on ocean turbulence together. And since they were off, here's Akira, by the way, and that was done by one of our students. Did you know that? And so the chief scientist, Osmedov, wanted to know if somehow we could arrange for a ship to come into the port of New York. I have no idea why he called me, but so I got in touch with the Department of State, and they actually said yes. By some, you have to remember this: the Cold War was raging, right? And so a ship came into Red Hook, tied up in a terrible place, so all burned out buildings and broken cars in the middle of the road. But this was their introduction to America. The ship pulled in, but on the other side you can see Statue of Liberty out there in the harbor. Anyway, the immigration people came in and they stamped the passports of 15 students, and Tom Wilson over here, I took 2 vans, SoMAS vans, and we drove in. We brought them out here. We had a day in this room. It might be another room, doesn't matter. It could have been in this room. Little vignettes of what we were doing in oceanography and what they were doing. And then one of our faculty, Eric, had a nice party in his house in Port Jefferson. And then Tom and I drove them back to the ship in the middle of the night. And then the ship left. And
we got a tour, didn't we?
yeah, well, I'm getting distracted already. That was quite a night, Tom. And
So that's where the vodka came from.
the captain. And then, of course, a week later, I got a call from the CIA, and that led to some tanglement with the CIA, which is a whole other story for another time. And Tom knows about that.
I still have their business card.
All right. So where was I? So there was a young scientist on board that ship. His name was Konstantin Koronchenko. And he came here, and we became friends. And out of that, then the chief scientist, Osmedov, and Akira got together, had a wonderful time, first time they'd ever seen each other. And so out of that hospitality we showed them, I got an invitation the following year to go visit the Soviet Union as a guest of the USSR Academy of Sciences. And we went to Moscow, and we went to what was then Leningrad, it's now St. Petersburg, and I met some of the giants in atmospheric and ocean sciences there. So, Konstantin, I hope where's the camera? This?
Yes. No, that's what it is. No.
Bye, Konstantin, I'll talk to you later, okay? Okay, so I get to make this visit, and then he said, look, Malcolm, how would you like to collaborate on some work in the Black Sea? I said, I know nothing about the Black Sea, but he told me a bit about it. It sounded very fascinating. And I'm just a country boy from Polynesia, and where the Europeans have only settled there and took away the Polynesians' countries from them, less than 200 years. And here's an ancient sea in Europe that's many thousands of years old. I mean, I'm talking about 7,000 to 8,000 years, the cradle of humanity in Europe. So I said, okay. So we actually got some funding from NATO. Can you believe this? In those days, NATO this was now about the year 2000. Soviet Union had crumbled. Russia was trying to build relationships with the West. So there was a NATO funding for collaboration between Russian and American scientists. Hard to believe these days, right? So we started working in the Black Sea. So that's how I got there. And so let's start showing some slides. Does this work? Okay, so there's the Black Sea. It's these are my collaborators. David Dietrich, unfortunately, He died last year. We'd worked together for 25 years. He is the father and author of this computer model we're going to talk about called diecast. Here's Konstantin, and these are two Bulgarians, husband and wife, who are sort of experts on the Black Sea, and so we sort of work together. This here is the logo of what's called the P.P. Shirshov Institute of Oceanology in Moscow. That's their big, like, NOAA lab, and it's still there today. This is kind of busy slide, but the top there is, that's just a little tribute to my colleague, does this thing work? No. David Dietrich. The last major work we did together is we published this book following the big oil spill, the Deepwater Horizon spill in the Gulf of Mexico, and it's called Modeling Gulf of Mexico Circulation Dispersion, but they said, no, you'll never sell a book like that. So we changed the name to Oil Spill Risk Management. It didn't make any difference because I got the royalties for last year. Guess how much? $2.32. Anyway, they wrote the co-authors were David Dietrich, myself, Konstantin, and my son Hamish Bowman. Now, what's all this? Well, this is what's called a first day cover. In the old days, before email, people used to send letters with stamps on. Remember? Some of you are older. And if it was a special commemorative stamp for some reason, there'd be something called a first day cover that would be mailed out from the headquarters, and these were sort of collector's items. And this came from the Shirshov lab in Moscow, and it was celebrating their research ship. It's called the research vessel Academic, I say Kurchatov, but Kurchatov, and this was the ship that came to New York City. Now, who was Mr. Kurchatov? Well, he was this gentleman here, if you can call him that. He was the father of the atomic bomb and the hydrogen bomb and nuclear power and particle accelerators, and actually the first nuclear-powered surface ship. So he was like the Robert Oppenheimer of Russia. So anyway, so here's Konstantin in Stony Brook. He came to visit me some years ago. Let's go on. So this is the Black Sea. So these are just some pictures I took. As I said, I've never been there. This was from the Google Images. And you can see, well, it's not black, right? The water's blue. So why do they call it the Black Sea? Well, I just want to say, look, this is an oil rig. So there's big interest in the Black Sea in oil and oil spills, and that's kind of partly why I'm involved in all this. But you can see there's some beautiful communities and buildings surrounding this inland sea. This explains for those of you who may be Greek scholars where the name came from, but it even precedes the ancient Greeks back to the Persians. And it means dark-colored, or it was really dangerous. A lot of the old ships, trading ships across the Black Sea, sank. Now, where is it? Well, here's a picture of here it is over here. It's a picture of Europe. But this map, there's some things seriously wrong with this map. Question, what are they? Can anybody see what's wrong? Yeah. There's North America. I mean, if that really was North America, we'd all be a bunch of Vikings sitting here today. So that's all. But this part's okay. And then, of course, it makes Russia look very small. But in fact, Russia's huge. It extends almost to the door over there. And in fact, geographically, it's the largest country on the planet. But there's the Black Sea. So it's completely contained and surrounded by 6 countries. Now, this is to get an idea of the size, I just at same scale downloaded these 2 images from Google Maps and comparing to the Great Lakes. So you can see this is Lake Superior, the largest freshwater lake in the world. And you can see, so it's big. It's about, well, it's 200 miles. So it's about 700 miles east to west, I suppose. And another difference is it's much deeper. The maximum depth is 2,200 meters, whereas Lake Superior is about 400 and a bit. So it's deep. And as I said, it's surrounded by Bulgaria, Romania, Moldova, the Ukraine, Russia, Georgia, and Turkey along the south coast here. So here's Istanbul, and this tiny little, you can't see it, this tiny little crack in the land, really, or it's called the Bosphorus. So here are the countries, as I just said, surrounding the Black Sea. Crimea this is Crimea here. Very important for the oceanography. It was annexed by the Russians in 2014 and still not recognized by the rest of the world. So this is the watershed of the Black Sea. It receives about a third of all the water, inland water in Europe, Western Europe. And so the watershed, is Munich. So it's Germany, Austria, Hungary, Croatia. This is an old map. Romania, etc. And all these rivers, they all drain into the Black Sea. So let's just look at some basic physical properties. Well, surface area, I'm not going to read all this, but east-west extent. The Bosphorus Strait. Now that's this tiny little connection through a complicated connection to the Mediterranean Sea, and that's the only connection to the Atlantic Ocean. The size of the shelf, the major rivers. Now this is important. Evaporation. These are cubic kilometers a year. I don't know if you can visualize what a cubic kilometer is. I can't, but it's a lot. So a lot of precipitation, more evaporation, but there's a net outflow through this Bosphorus Strait into the Mediterranean, and so you can do a water balance. So you have rivers coming in, you have rainfall coming down, you have evaporation going up, and you have loss through the Bosphorus. So it should add up roughly, right? Well, these numbers I gave you don't add up. They're from different authors at different times, but they're within about 13%. Now here's interesting. Even though this is a gigantic inland ocean, over 700 miles across, the tides are negligible. The tides are from 2 to 9 centimeters, the size of my hand. You might say, why is that? It's huge. Why doesn't it have tides? Well, the reason really is, when the moon goes over, the gravity doesn't suck water up. It pulls it from the sides. That's how the tides come in. And so it's got half the circumference of the Earth. It's pulling water sideways and accumulates where the high tide is. So that's the reason it's not even big enough to have that kind of a pull. So it's basically tideless. There it is there. The surface temperature, there's a large annual range. It depends where you are. I mean, it covers quite a range of latitude. The southern extent's about 41 degrees, which is the same as us here. But up in the northwest, it actually ices over in winter. But in summertime, in the surface, it can get up to 23 up to 28. Gets up to about here on the continental shelf. Gets up to about in the mid-20s. So it's not that different. The bottom temperature, you'll see in a minute, is very stable, about 8.5 C. And the water on the surface, though, is 17. It's 17. Why is it so low? Well, it's so low because of all the rivers coming in, particularly the Danube River in the west. But there's a big contrast, and this Bosphorus Strait is not. It's really like an estuary. It's at a narrowest width is only about 2 kilometers wide, but there's a very strong 2-layer flow. So the surface water is flowing out southwards, but the bottom water from the Mediterranean origin is coming in. They don't quite exactly balance, just like Long Island Sound doesn't balance, because you've got the rivers coming in, so there's more going out than coming in. What's this? Well, there are no tides, but there's what's called sashing. Sashing is just sort of slopping around. If you get a sudden gust of wind, it can set up rocking motions, and it's called a standing wave. And if this is a bit of a diagram, this could be the Black Sea from east to west. And a standing wave is nothing but a progressive wave going that way, bouncing back and coming back on itself, and the two interfere and create the standing wave. So these are quite common. I did some calculations last night. The period of these oscillations is maybe 5 to 8 hours. You get this in the Great Lakes as well. You've probably looked at them, Roger, have you? In the Great Lake Superior? No? Okay, so this is the Bosphorus. I mean, historically, over the centuries, over the millennia, this has been a very strategically important, and it still is today, both militarily and politically. Here's the Bosphorus. It flows in the Sea of Marmara, down through the Dardanelles, where there was a terrible battle in World War I between the Turks and actually the New Zealand and Australian troops. It was a bloodbath organized by Winston Churchill, and the Allies lost. But anyway, so here's the Aegean Sea that goes into the Mediterranean, Oh, and I have to make one little diversion if I got time. Two of Roger's professors at Columbia, Ryan and Pittman, wrote this book called Noah's Flood. And Roger and I have talked about this a little bit. But the basic theme was that during the last ice age, sea level was much lower. Apparently the Mediterranean Sea pretty much dried out. The Black Sea was 500 to 700 feet lower than it is today, and it was a freshwater lake. And this connection through the Bosphorus Strait was a dry land. It was a bridge, so there was no connection. And so what they claim happened was that during after the end of the ice age and sea level started to rise, the Mediterranean filled up, and then the Bosphorus Strait broke through. So there was this massive inflow of Mediterranean water, which was equivalent, they claimed, to about 30 Niagara Falls, and this went on for maybe 30, 40 years, and it brought up the Black Sea up to where it is today. Now, how do they know this? Well, if you go down and you take, there's evidence of riverine valleys in the sediments deep down. Apparently, some of the seashells deep down are freshwater species, are the ones between, say, 500 feet in the surface are salt water. And so they claimed this might have been the historical impetus for the study in the Bible, in Genesis, of the Great Flood. And that they claim that as the sea level rose, all those ancient communities around the perimeter of the freshwater Black Sea at that time all fled in different directions as far west as France even. So it's too much to read there, but there's a bunch of books on all this. People have various theories about what was the Great Flood actually, and what actually happened. So we'll go on. But in the year 2000, I think the summer of 2000, also maybe 2001, the National Geographic Society funded Robert Ballard, the co-discoverer of the Titanic, to go to the Black Sea using all the same equipment, underwater acoustics and camera and stuff, to see if they could find evidence of ancient villages, which they did. And can't read that, but they concentrated their efforts here on the north coast. It's called the Sinop Peninsula, north coast of Turkey. Oh, by the way, since 6 countries claim the sea, it's like a pie, like a cherry pie, but this is the middle, and they each have a slice. So it's very difficult working there. If you go from one slice to the next, you've got to get permission to travel. And so they did bottom cores around here, or up here. Oh, this is Ryan and Pittman, but the Ballard, and this is a sort of picture of maybe the breakthrough at the Bosphorus and the water's pouring into the Black Sea. Well, the National Geographic got very excited about this. Ballard got very excited. They had blogs on, guess what, they had blogs back in the year 2000 on the internet, and they had discovered this ancient village. It was a roof of a building. They got permission from the Turkish government to pull it up. They found it was not an ancient village at all, but it was a roof, a cover for a hold of a ship that had blown off. Anyway, but there were apparently beaches and stuff that are down there, so they believed there was something to it. But the thing about the Black Sea is, because of this great stratification between the heavy, salty Mediterranean water creeping in through the Bosphorus and then sinking straight down, and the surface waters from the Danube and the other major rivers on top, it doesn't mix, at least not below the top 50 meters. And so the bottom waters slowly have gone hypoxic and anoxic, so it's a hydrogen sulfide dominated system down there. But this is a photograph. I'm not sure this is Ballard's photograph, but it was a National Geographic photograph of an old ancient shipwreck sitting on the bottom in deep water. And it's amazing. If you look at the detail, this could be 2,000 years old. Look, it looks like ropes and carvings and goodness knows what. So everything is basically preserved.
So how low is the oxygen level?
0. You'll see that in a minute.
No, the depth.
Well, the depth, I'll show you in a minute. Mary can tell you, but it's like below 100 meters.
Bottom water sulfide is hundreds.
You'll see a DO plot in a minute. Now this is the modern day bridge across the Bosphorus Strait, and I don't know what the heck this is. It looks like a floating city. It looks like a hotel or something. I don't know what it is. Yeah, it's 2 barges there, but it must be 2 barges. It must be an oil rig or something. Well, what's going on today? Well, there's, because of the trouble in the Ukraine, There's a lot of saber rattling going on. This is the Russian destroyer, I guess. I don't know what these huge things are. They look pretty menacing. Rocket launchers. There's an American ship that got permission, U.S. naval destroyer, the Carney, last year made its way with carefully staying in Turkish waters. So, but let's get on to some oceanography now. So what is this? Well, this is an amazing photograph. I enhanced this myself. I just used the simple photo imaging software like Picasa, a Google product that some of you may use. And this is a satellite that was up on 11th of June. And if you look at the Black Sea, it doesn't look anything like those placid blue photographs I showed you in the beginning, but it's a massive swirling eddies. And it range from something that looks like, you see these hammerhead vortices? That's thought to be due to a sudden gust of wind blowing like this, and it sets up these swirling waters. But all around the coast, it's gigantic. It's just a beautiful, lovely confusion of eddies. This is 2 days later. It hasn't changed much. So these eddies can last for months. There's a famous one here you'll see in the east called the Batumi. The city of Batumi in Georgia is about here. This is the Crimean Peninsula. There's another famous one called the Sebastopol Eddy, which is just off the coast there, off the city there. This is kind of a schematic diagram, which is a standard thing you'd find in encyclopedia. And so what you see is this. Remember, there are no tides, but there's this current that goes around the whole basin in a counterclockwise direction. It's called the rim current, for kind of obvious reasons. And remember, it's just like here. There's a continental shelf, and then the shelf breaks about here, and then it shoots down to 2,200 meters. But this major circulation can be thought of as a western gyre and an eastern gyre. And it's very persistent. It changes seasonally. It's strongest in summer when the stratification is strongest. And this is where, you don't have to see the detail, this is where the delta of the Danube River flows in, carrying a lot of water from Europe, and that freshens this whole area. It's very shallow up here. This is called the Sea of Azov. There's a little strait there as well. And there's the tiny little Bosphorus Strait. You can't see it. I'm going to tell you in a minute.
So what's the brown? What is the brown?
I don't know. I don't know what they are. Points of interest.
What's the latitude?
The latitude here is 41. It's the same as Stony Brook. So, and it goes up to about, I think, 48, 49. Okay, so this is just like from an undergrad textbook showing what, if you can imagine, this was the Bosphorus Straits. There's bottom water's coming in from the Mediterranean, and it pours down over the slope, and it pools at the bottom and just stays there. In some ways, it's like a fjord. It's very similar to a fjord, where you have a sill at the mouth of the fjord, and a lot of hypoxic or anoxic water inside. But the flow actually in the Bosphorus is a strong two-layer flow, out in at the bottom and out the surface. And so that's the region. This is the region, this huge region below 100 down to 2,000 meters, which is pretty much anoxic. And it's been like that for thousands of years. So there's Istanbul, Bosphorus Strait. So that's only that tiny little channel. Strait is the only connection with the ocean. And you can imagine that, even though it looks so beautiful in those early photographs, that there's a lot of pollution there from all those rivers and those 6 countries. Now here's my only plot. So of the oxygen. So DO is this blue line. So this is the top. This is not even a linear scale, but this is the euphotic zone down to about 50 meters. And this would be in summer probably, but here's the DO. So it actually increases and then it drops and goes to 0. This is nitrite, nitrate, ammonia, hydrogen sulfide. That's the way it is. So, and it's all kept that way by the strong density stratification of the seawater. Now, what does it look like in the vertical? This is the plot. I don't know if you can see. You don't have to read the numbers. This is depth, 0 to 100 meters. So it's the top 100 meters, And this is time, January, 12 months, 13 months back to January, February the next year. And these are contours of temperature. Look at the bottom one. So in the winter time, just like around here, there's a lot of mixing, and it's almost mixed down to, say, 80 meters. And then as we move into the spring months, it starts to stratify. And so then we get the strong thermocline. And this is the water trap below it, about 8 degrees. And the whole, everything below 100 meters is about 8 degrees and stays there. And then in the fall, you have the breakdown of the and heat loss of the atmosphere, and then it becomes well mixed
So
again.
where is that station taken?
It's point A. It's right there. Okay. So that's an average, because as you'll see in a minute, the water's forever moving around. So it's
Well, the depth of the interface is really different.
Yes. Yeah. So that's just point A. So this is the, I won't go into detail, but this is our model, this die-cast model that my colleague David Dietrich created over his lifetime. And just trying to match that. Okay, so here's these eddies that we're going to talk about now are so prolific and so pronounced they even have names, even though this suggests that they're fixed in time and space, but you'll see in a minute they're not. This is the Batumi Eddy after the city of Batumi, the Sebastopol Eddy, the Bosphorus Eddy, etc., the Western Gyre, the Eastern Gyre. So this inland sea is so energetic, and these eddies are of a scale that equal anything the Gulf Stream can produce. And I've done work in the past in the East Australian current. They have gigantic eddies, but this actually is so interesting. And because it's surrounded by land, it contains everything that can't, so the currents can't drift off. Getting back to Chris's question, what are the driving forces? Well, there's two actually. The first one is simply the inflow of water around the perimeter freshens the water of the sea. It stands higher, right? And so if you look at sea surface height, it's highest around the edges and it's lowest in the middle. And this is what these are centimeters. So this is like -8 centimeters with respect to mean sea level, and this could be +12. So there's maybe 20 centimeters. Of course, a huge difference, but that's enough to drive surface geostrophic currents, which are balanced between pressure gradient and Coriolis, and that is and has to be, a primary driving force. And we want to do some experiments by just turning the wind off and seeing what we have. And so this is from the die-cast model. This is a snapshot. And so here's the giant eddy that's just been spun off from the Crimean Peninsula, Batumi Eddy, Bosphorus Eddy, etc. And it's all spinning around counterclockwise.
Why do those eddies form?
Well, I'm going to get to that. Okay. So this is from a Russian oceanographer, a schematic. This is a snapshot of what we got, and I think it's pretty realistic. So I'm not going to go into the model, but for those modelers in the audience, it's a Z-level hydrostatic model, 20 vertical layers, but they're not all the same thickness. The top layer is very thin because that's where most of the action is, the 1 meter. The bottom layer, way down there, is 32 meters thick. Horizontal resolution is 1/12 of a degree, which is 5 nautical miles, say 5.5 land miles. Time step of 12 minutes. The equations are standard, but the art of modeling is not so much the equations that everybody knows about, is getting the darn thing to work, and to work realistically, and to have to cope with bad data. You can't just sit in your office and turn it on. I haven't got to the winds yet, Chris. You've got to put what's known as the climatic information in there. In other words, the temperature and the salinity that people have gathered over the decades and from whenever oceanographic measurements were made. So you have to have some idea of what the temperature and the salinity structure is before you turn this darn thing on. Otherwise, it'll just sit there and do nothing. So, okay. So now look, here's a nice little animated GIF. Now what are we looking at? We're looking at what is these colors? Colors is sea surface elevation. Okay, just like the Gulf Stream stands a meter higher than the Atlantic. These eddies are maybe 20, 40 centimeters higher in places, And this is going through a year, pretty much a year. This is Julian day, so it starts on January the 1st and then just repeats. So, Chris, sorry, I didn't answer your question, but also important is what's called the curl of the wind stress. So the prevailing wind patterns reinforce these density-driven forces. So once again, you see, Barbados, well, what causes these eddies? Well, this is a huge. This spot is hugely important because it's a combination of bottom friction and also the very steep drop-off in the shelf and a strong current, maybe 1 meter up to 1 meter per second, that stretches these eddies and causes them to wind up. And Darcy knows all about ballet dancers pirouetting, right? You know, when you can come show us if you like. Now, if you're spinning around, then you put your arms down on your side, you'll spin faster. So that's a very simple explanation. We'll come back to this Batumi eddy in a bit because it's not just as simple as all that.
So, excuse me.
Yeah.
That's really the surface layer down to the incline.
Yeah. I'll take you down deeper, sir. Just hold on. You're very impatient. So these are the winds. So in winter, these are cyclonic winds. They're spinning that way over here, and down further south, the anticyclonic. So that gives a twist or a curl to the surface circulation, which works with the densities. Now, I don't know what this is exactly, but I suspect it's something called Vorticity, which I'll talk about in a minute. But this is from a famous Russian oceanographer in Moscow, Zetsipin. I had a chance to meet in Belgium a few years ago. But you can see how the point of this slide is, the question is how deep do they go down? Well, this is 250 meters, so they obviously go down maybe 350 meters, so they're shaped like a huge carrot, if you like. Now this is a beautiful picture. This is surface salinity in parts per thousand, or PSU. And once again, at the count at the top is running in days, so it's best part of a year. So it just shows.
Really makes eddies, doesn't it?
Pardon?
This model really produces eddies.
Yeah, well, that's why I'm interested. I'm very interested in eddies, things that swirl around. And, but you'll see some more in a minute. But this is a place to watch. Here's a gigantic. Now that's curling that way, see, and this one's curling that way. So it's not just cyclonic versus anticyclonic. Now this is the same thing, but this is at 4 depths. This is the one we just saw. This is 50 meters, 100, 200 meters, just to give an idea what's happening down there. What's the circulation? How deep? This is all model, remember. This is not observation. So obviously this is very vigorous at the surface. And we go down to 200 meters, well, the first thing you notice that this is all dry land now, because see, this is the Danube River coming in. See this blue water? That's low salinity Danube River water. Here's the poor little Bosphorus doing its best to suck some water out. But down to 200 meters is barely moving. So not only are these huge eddies swirling around and traveling around, but they're also tilting as they go. Now this is interesting. I'm going to just spend a couple of minutes talking about vorticity, because it's a beautiful word, don't you think? Vorticity. I mean, it suggests vortex and things that are really spinning around and important. But I want to show you something. It's sort of off the subject a little bit, but when I first came here, there was a professor of mechanical engineering called Edward O'Brien. And Edward O'Brien, the only person in this room who knows Edward O'Brien is Bob over there. And he was actually on the search committee that hired me. But anyway, he was an Aussie, and he was a great guy, except he had a very strange accent. But he taught me what vorticity is, because I hadn't got a clue what it is. His name was Edward O'Brien. He married a beautiful Cuban woman of African descent. I think they had 6 or might have been 12 children. Beautiful. And Barbara, I saw these as kids, but one of them grew up to be a very famous person. Her name is Soledad O'Brien. And some years ago, she was a news anchor on CNN, I think CBS, and she traveled around the world. and became quite famous. This book is good for, stop me, Malcolm, I'll get carried away, but if you're a woman in science and just women in professions, this is a great story. And it, you know, Ted O'Brien and his Cuban wife, in retirement years, they live in Manhattan, looked after her two children so her career could progress. So why am I telling you this? Well, I'm telling you this because Ted O'Brien told me what vorticity is. And I'm just going to give you a very quick demonstration. It won't take a minute. He said, Malcolm, what you do, you get two matchsticks and you put them, cross them like that, right? Now, pretend I'm a blob of water, nothing more, right? So I'm traveling along. Now, if the water that I am happen to be turning as I travel, round and around itself, not round the room, it's got vorticity. Or it could be, if it's just like this, we're just all just going along together, it's got zero vorticity. Or if the currents over here are strong and the currents over here are weak, it'll turn that way, right? So it's got negative vorticity. That's what it is. It's twisting itself. You might say, well, who cares? Well, it's very important in ocean dynamics because we live on a rotating world. Even the Earth has vorticity. We're going to run out of time, but look, I'll show you something. Supposing my little matchsticks are on the Earth, okay? There they are. Come on. All right. You won't forget this, right? All right. Now there's no, in this, you can see it, there's no cross matchsticks. They're not moving, but as the Earth rotates, and if I look down, they're rotating by themselves as the Earth goes round. So actually the Earth has vorticity. It's called Coriolis. What?
It's called vorticity, it's not called Coriolis.
Well, people know what Coriolis is. Coriolis was a French mathematician who studied this. All right. I know that, Charlie. Look, stop interrupting. Anyway, but by the way, which way does the Earth rotate? This way? Or this way? Who say it goes clockwise? Half my students don't know. So it goes this way, it goes counterclockwise. But if you go underneath where I come from, which way is it turning? So it depends on your point of view. Most textbooks are written by authors who live in the Northern Hemisphere, so they've never seen this effect. Right? What I'm trying to tell you is that things are opposite in the Southern Hemisphere. So while in the Northern Hemisphere, like a cyclone or a hurricane spins counterclockwise, down under they spin clockwise. All right, enough for Ted O'Brien. Let's carry on. So I'll never forget that lesson he taught me. And so that's something amazing when you think about it. I wouldn't be here perhaps if he wasn't on the search committee, and she wouldn't have been here if he wasn't her father. So we have a connection. It's true. Now what's this? Oh, don't waste your time, but this is just a picture I snagged this morning. This is like a wheel, just a solid wheel, like a big pank, like a bit of pizza rotating around. And so as you go from the middle to the outside, it goes faster. And so if you had a matchstick, think of looking down on this matchsticks, they would twist. So it's got positive vorticity. Now this is not a circle. This is all water or airflow going in the same direction. But see, it's slow here and it's fast here. So we call that horizontal shear. So if you were a blob, if you were the matchsticks, you would be rotating as you go along. Negative vorticity. That's not right, it's positive. But don't worry about it. We'll fix it later. Now what about this one? This could be like a tornado. Very fast in the middle, and as you go out, it's turning slowly. So if you were a matchstick here, because it's going fast here and slow here, you'd actually turn this way. So that would give you... No. This is a special, just for this only, where the speed is proportional 1 upon the radius. It doesn't rotate at all, it goes like that, zero vorticity. So it's not what you think it is, but it's very interesting. It helps solve mathematical problems. Now this is the beautiful picture. This is relative vorticity for the Black Sea. It's the same. You're looking at salinity a few minutes ago, but this is, well, I think that's beautiful. I think we should have a special exhibition at MoMA. Don't you think that would attract a lot of attention? But what do you see here? You see, this is day 180 is midsummer coming up. There's more organized structure in the summer, but in winter, there's a lot of looks like just like little speckly patterns. It's more disorganized. Some of it's noise in the computation, but you still see these huge eddies swirling around. And just because an eddy's spinning one way doesn't necessarily mean it's got one sign of vorticity. It can have both, or one after the other. This is the various depths. Constantine, thank you, Constantine. He did this last night. He stayed up all night. So this is at 50 meters, 100, and I think 200 again. So once again, you can see at the surface you have blue or red and yellow. They're opposite signs. But as you go down, the strongest ones are the anticyclonic or the clockwise spinning eddies. And by the time you get down to 200 meters, there's no yellow at all. So we can learn something about the structure from these plots. Running out of time, but this is the Sebastopol Crimean. This is the place where these huge eddies are generated, and they last months as they get carried around counterclockwise by the current. That's the vorticity. Well, I have to show you this. Now, where the heck is it? This is just 152. These are what's called von Karman vortex streaks. Von Karman was a German fluid dynamicist. What we're looking at here, we're looking down on an island. That blue thing is an island, and the water's flowing from the east, steady flow, until it hits the island. And then the flow has to go around the island, of course, and then it gets into a sort of repeating pattern. And these are called vortex streaks. So these eddies are generated on the sides of the island, get carried off, they grow, and it's just one of the beautiful things of nature. This is just another example. I actually had a project here years ago in Barbados with Bob, what was his name? Cowan and Kamazima, looking at dispersal of fish eggs from Barbados in the Caribbean Sea. And you think of these little dots as larvae of reef fish that have to get off the island for some months, otherwise they get eaten by the big fish. But these are just beautiful patterns. So we better stop there. I could watch this all day. And how do you stop it? Okay, so.
Top right. Further right.
What? Okay, so you've just seen that. Now this is an example of a real one in atmosphere. These are clouds, and this is looking down at Guadeloupe, and you can see the winds come this direction. You see these beautiful eddies that are generated. And the reason I'm showing you these is that nearly finished. The reason I'm showing you these is that those eddies that generate off the Sebastopol eddies, it's like half a vortex streak. It's not an island, but it's a peninsula sticking down, and the flow goes past, and it's spun up, and then they shed. So we've done some modeling of these with David, and it's very interesting. Anyway, just finally, we're trying to get Constantine to come here next year under maybe a Fulbright scholarship. You still there, Constantine? We're trying. And our experience with modeling the oil spills in the Gulf of Mexico, we're going to apply to the Black Sea. And there's a lot of oil on the north east coast here. And this is just a simulation of supposing there was a oil spill right here, and we just track it. It's a bit fast, but for 50 days, and you can see that stuff gets carried all around, and there's more going on than the eye can see because it depends a lot on the density of the oil, on the spill. Is it buoyant? Is it coming from the bottom, or is it being released from a ship that's got a leak? And then you've got evaporation, you've got fractionation going on, you've got sinking of some fractions and evaporation of others. So it's complicated, but you can just see that. And when in conclusion, we predict increasingly well the dynamics of the Black Sea, but it's impossible to predict in the sense of a weather forecast what's going to happen, say, in the Black Sea, say 3 weeks from now, 4 weeks from now, maybe a month from now even, in detail. You know, there's an element of chaos in nature that no matter how hard you try, you can never get a perfect weather forecast 10 days from now, right? It's even harder in the ocean because, for many reasons. In the Black Sea, of course, you have the constraint of the coast, sort of with its arms around the water, but, you know, if the Russian Navy said, where do we send the cleanup ship, you know, when we say here, well, it may not be right. So that's what we want to look at. And just to finish off, this is just a beautiful picture, I think. It's looking east. So this is the Danube here. This is the Crimean Peninsula. This is the north coast of Turkey. These are just this beautiful field of eddies. That's the end. Thank you. Mary?
So there have been some actual geochemical data that related to particular spills like Chernobyl. I'm sure the Germans have done stuff about it since a lot of the oil development is in the Danube Delta there. Have you compared your results to any of those kind of data, or are you just doing it independently with Russian data? Because there's a lot of people besides the Russians working on the Black Sea.
Well, this has been sort of an advance since the early, the first decade from about 2000, 2002. So, you know, I tried to get some NSF support. It didn't come through. It's very difficult doing measurements there. So I got involved in other things. But now we're trying to kind of crank this up again. And
well, I'm just thinking as to support your theories about what's going on.
Yeah.
I think there is a lot of data that you're not using.
I'm sure.
That talks about
Yeah, I'd like to know about
surface spills.
Yes, well, thank you. We'll look that up.
What's the resolution of the model?
1/12, 5 miles. 1/12 of a degree latitude. So it's 5 miles. You might say, well, that's huge, but you're talking about something that's like 750 miles wide. Now, I should say that the model is nested, so in the Bosphorus Strait, where it's only 2 kilometers, you might say, well, how it won't work. Well, you nest with a high-resolution model there, and you join them together. And we get them running together, not just separately.
The other thing that makes the Black Sea difficult to work in and also interesting is that now that Russia has taken over Crimea, it's become again the warm water port of the Russian Navy.
Yeah.
Which is why nobody could do any work in the Black Sea for 30 or 40 years
Yeah.
during the Cold War.
Well, we're back to that.
And so I think that's diversifying your colleague group
Yeah.
and focusing on things other than the Crimean coastal area might
Yeah.
be used.
Yeah. It's a lot of good sense. Thank you.
Thank you, Malcolm. There are no more questions, or you can keep talking on the lunch.
Every woman in the room should read this book. And men, too. Thanks.